Now we enter power flow computation. Power flow is the foundation of many power system tasks. Before we can evaluate security, dispatch generation, plan network expansion, or analyze voltage problems, we need to know the operating state of the grid. A power flow calculation answers a basic question. Under given injections and network parameters, what are the bus voltages, phase angles, branch flows, and the losses? In this part, I will first explain traditional methods under the Newton paradigm. These methods write the physical relationships into equations and solve them iteratively. Then I will discuss data-driven methods under the Kepler paradigm. These methods learn a mapping from inputs such as load, generation, topology, and line parameters to outputs such as voltage and flow. Finally, we will discuss fusion methods, especially physical information, neural networks, and graph-based models. The key issue is reliability. Power flow results are not ordinary predictions. If the result violates Kirchhoff current law, Kirchhoff voltage law, or network power balance, it cannot be used for dispatch or security assessment. Therefore, intelligent power flow computation should not only be fast, it should also be physically consistent. When listening to this section, please keep two questions in mind. Why are traditional power flow methods reliable? And why do new power system scenarios require acceleration and enhancement through intelligent computing? Power flow is also the entry point for many higher-level applications. Contingency analysis runs many power flows. Voltage control depends on power flow sensitivity. Distribution automation and transmission distribution coordination both require repeated state calculations. Therefore, even a moderate improvement in power flow speed or robustness can have a large system-level effect. This page explains why traditional power flow is a nonlinear algebraic equation-solving problem. In an AC power system, active and reactive power are nonlinear functions of voltage magnitudes, voltage angles, conductance, susceptance, and trigonometric terms. That is why the equations cannot usually be solved by one direct linear calculation. The page lists two representative methods, the backward-forward sweep method and the Newton-Raphson method. The backward-forward sweep method is often used in radial distribution networks. It first sweeps backward from terminal loads toward the source to update current or power, and then sweeps forward from the source to update bus voltages. It is intuitive and efficient for radial structures. The Newton-Raphson method is more general. It linearizes the nonlinear equations around the current operating point, builds a Jacobian matrix, and repeatedly corrects voltage magnitudes and angles until the power mismatch becomes small enough. The Jacobian matrix is not just a mathematical object, it represents the local sensitivity between state variables and power mismatches. This is why it is central to convergence and numerical performance. Traditional methods are valuable because they are physically meaningful and theoretically mature. Their cost, however, lies in repeated iterations, Jacobian construction, matrix factorization, and linear equation solving. For very large systems, frequent topology changes, or online applications, this computational burden becomes a strong motivation for intelligent acceleration. When you see the Newton-Raphson method, do not think of it only as a numerical trick. It is a structured way of using local linear information to solve a nonlinear physical problem. The mismatch vector tells us how far we are from balance, and the Jacobian tells us how a small change in state variables will reduce that imbalance. This interpretation is useful when designing learning-based initial value or correction models. This page summarizes the challenges faced by Newton paradigm power flow methods. The first challenge is convergence. When a system has high resistance to reactance ratios, weak grid conditions, poor initial values, heavy loading, or unusual transformer settings, the nonlinear equations may become difficult to solve. This is especially important in distribution networks and integrated transmission distribution analysis. The second challenge is computational burden. In the Newton-Raphson method, each iteration may require updating the Jacobian matrix and solving a large linear system. When the grid contains thousands or tens of thousands of buses, this is expensive. The third challenge is numerical stability. If the system is close to its operating limit, or if the initial guess is far from the solution, the iteration may oscillate or fail to converge. These issues become more serious in new power systems. Distributed photovoltaics may reverse power flow. Electric vehicles may create fast-changing load patterns. Flexible devices and power electronic interfaces may change traditional network behavior. I am not saying that traditional methods are obsolete. They remain the backbone of power system analysis, but they need support. Intelligent computing can provide better initial values, identify risky scenarios before iteration, approximate repeated calculations under physical constraints, and help the solver focus computational resources where they are most needed. In practical operation, convergence failure is not only an inconvenience, it can delay security assessment or hide a dangerous operating condition. This is why intelligent methods that predict convergence difficulty are valuable. They can warn the operator before the solver fails or choose a more robust solving strategy for difficult cases. This page moves to power flow computation under the Kepler paradigm. The core idea is to learn the mapping from operating conditions to power flow results using data. Inputs may include load levels, generator outputs, topology, network parameters, and device settings. Outputs may include bus voltage magnitudes, voltage angles, active and reactive branch flows, or convergence labels. Deep neural networks can approximate this mapping after seeing many historical or simulated samples. Convolutional neural networks have been used when data can be arranged in a regular structure. However, power systems are naturally graphs, buses are nodes, branches are edges, and electrical coupling follows the network topology. Therefore, graph neural networks are especially relevant. A graph convolutional network can aggregate information from neighboring buses and lines, allowing the model to learn spatial coupling in the grid. The advantage is speed. After training, the model can produce a result through a forward pass much faster than an iterative solver. The limitation is generalization. If the training data do not cover a certain topology change, heavy load condition, renewable fluctuation, or rare contingency, the model may produce an inaccurate or infeasible result. Therefore, pure data-driven power flow should not be treated as a full replacement for traditional methods. It is more realistic to use it together with physical constraints, topology-aware structures, and post-checking mechanisms. Graph learning also gives us a language for transfer. If a model learns only a fixed vector order, it may break when the grid changes. If it learns through nodes, edges, and message passing, it has a better chance of adapting to topology variation. Of course, this is not automatic. The training design must expose the model to enough structural diversity. This page is one of the key pages in the power flow section. It compares two fusion modes, a guiding mode and an embedding mode. In the guiding mode, physical information is introduced mainly through the training objective. For example, topology-gated physical information neural networks, or TGPN, include power flow residuals and topology constraints as regularization terms. The network is punished when its output violates power balance or network laws. In simple words, the physical equations act like a teacher during training. In the embedding mode, physical information is built into the model structure itself. The model-driven graph convolutional network, or MDGCN, does not only add residual terms to the loss function, it uses the network topology, linearized power flow relationships, and electrical connections inside the graph propagation process. In this case, the structure of the neural network carries physical meaning. The difference is important. The guiding mode adds physics to the objective. The embedding mode adds physics to the architecture. Both try to solve the same engineering problem: how to make neural network speed compatible with power system laws. If the model is only fast but violates Kirchhoff laws, it is not useful. If the model is physically correct but not faster than traditional solvers, its value is limited. The fusion method tries to obtain both speed and credibility. A practical hybrid workflow may look like this. The neural model quickly predicts a candidate solution. Physical residuals are checked, and the conventional solver performs a few correction iterations if necessary. This workflow does not force us to choose between AI and traditional solvers. It lets each method do what it is good at. This page summarizes the research content for intelligent power flow computation. First, we need neural network architectures that can both judge convergence risk and compute power flow results. In practice, it is not enough to output voltages. We also want to know whether a scenario is likely to be difficult or unsafe for traditional solvers. Second, physical information such as Kirchhoff current law, Kirchhoff voltage law, topology, network parameters, converter models, and AC grid models should be embedded into the learning process. Third, sample selection is crucial. Training data should cover a wide range of operating scenarios, including normal cases, boundary cases, and topology variations. Fourth, generalization must be tested. A model that works only on one fixed topology has limited engineering value. Fifth, incremental learning is needed. Real grids change, lines are added, parameters are updated, loads shift, and devices are replaced. A useful intelligent model should be able to update itself without being rebuilt from zero every time. The conclusion of the power flow section is clear. Intelligent power flow is not a disconnected offline predictor. It should become a trustworthy online computing module that can accelerate repeated analysis, support traditional solvers, and keep the result physically meaningful. For this reason, the best evaluation of intelligent power flow should include more than mean absolute error. We should also report power balance residuals, voltage limit violations, line flow violations, convergence assistance, and performance under topology changes. These metrics connect the learning model with actual engineering use,